In the previous video, we mentioned how electronegativity is arguably the single most important concept in Chemistry 11, and this is because electronegativity is used to explain how elements form bonds with one another. And this is done by taking the difference in electronegativity between two elements that form a bond, and the short form of this measurement is what we call delta En. And as you know from math, delta is a variable or an operation that means change or difference in. Now, in order to calculate the difference in electronegativity, first we actually need to identify what the electronegativity constants are using the periodic table. So if we want to calculate the electronegativity difference in sodium chloride, we can take sodium's electronegativity of 0.9 and chlorine's electronegativity of 3.2. So let's just write out each of those here. Chlorine's is 3.2 and sodium's is 0.9. And in order to calculate the electronegativity difference between the two, all we need to do is some simple subtraction, and we can see that the difference in electronegativity between the non-metal chlorine and the metal sodium is 2.3. Now, that was easy, but the most important thing is, well, what do we actually do with this information? Now, in order to explain how electronegativity is so useful in explaining how elements form bonds, it's easier to visualize what exactly is happening here. So what we're doing here is we want to actually show how the pair of electrons that involves a bond actually moves and where it is located in relation to the sodium atom and the chlorine atom. Now from Science 10, you know that as a metal and a non-metal, sodium chloride are joined together by an ionic bond, as are pretty much every metal and non-metal combination. Now, you should remember that because sodium only has one valence electron, while chlorine is one electron away from a full valence shell, the unpaired electron from sodium is transferred from sodium to chlorine. In other words, the unpaired electron is transferred from the element with the lower electronegativity that is very poorly able to hold onto its own electrons and take electrons from another element, and this electron is transferred to the element with the higher electronegativity, or the element that is much better at gaining electrons, and the result of this is that sodium loses one electron while chlorine gains one electron. Electronegativity is just the justification behind how this happens. So, if this dotted line here represents the exact midpoint between the sodium atom and the chlorine atom, the electrons that make up the ionic bond would both belong to chlorine because sodium has freely given its electron over. Now, because of the fact that sodium has fully lost an electron, we can label sodium as having a positive charge. Likewise, because chlorine has fully taken sodium's electron, we can label chlorine with a negative charge, and this is true of any pair of elements that form an ionic bond, and of course the charge is determined by whether the element has gained electrons, in which case it would be gaining negative charge, or whether it has lost electrons, in which case it would be gaining positive charge. Now, technically, we can look at this movement of electrons even in bonds that are not ionic bonds. And of course, you remember from Science 10 that when electrons are shared between the two elements that form the bond, they form covalent bonds instead of ionic bonds. And what we're going to do is we're going to start with the simplest example of covalent bond, the bond between hydrogen gas. In other words, the bond that is formed between hydrogen and hydrogen. And if we check the periodic table, we can see that hydrogen's electronegativity is 2.2, but that doesn't really matter because 2.2 subtract 2.2 is obviously 0, so the difference in electronegativity here is 0. Well, what exactly does this mean? Well, if we ask kind of a silly question, which of these hydrogens wants the electrons in the bond more, the hydrogen on the left or the hydrogen on the right? Now, most of you will recognize that this is a silly question because if the elements are the same and their electronegativities are the same, each of the elements wants the electrons equally, meaning that the two electrons that make up the bond will not be closer to either hydrogen and will basically be split entirely equally down the middle, also called perfect sharing. Now, this is an example of what we call a nonpolar covalent bond, and we'll talk about what the word polar means in the context of bonds when we look at the opposite of a nonpolar covalent bond. And the justification of a nonpolar covalent bond is a covalent bond that involves the sharing of electrons basically perfectly equally, and if not almost perfectly equally, in which case delta En is not exactly 0, but is very, very close to 0. So for example, if we look at the bond between carbon and hydrogen, so if we take a look at carbon's electronegativity constant, which is 2.6, we can do a quick delta En calculation here. 2.6 minus 2.2 is 0.4, which is relatively small. So in this case, because carbon has a very slightly higher electronegativity than hydrogen, now the electrons are not perfectly exactly in between the two, but are actually slightly closer to carbon because it has a greater ability to attract electrons and pull electrons toward this side. But because the difference is very, very small, specifically the difference is less than 0.5, any covalent bond with a difference in electronegativity that is less than 0.5 is considered nonpolar covalent in nature, meaning that even though the electrons are not shared perfectly equally, they are not closer to one element or another in order to make a difference. But this is not true, as we will see, with bonds between hydrogen and nitrogen or hydrogen and oxygen. These are both examples of polar covalent bonds, and we will see why when we take a look at the electronegativity difference. So let's go ahead and find the electronegativities of nitrogen 3.0 and oxygen 3.4. So what we're going to do is a delta En calculation between nitrogen and hydrogen. 3.0 minus 2.2 comes out to 0.8. And once again, if we visualize this, what we are saying here, because 0.8 is greater than 0.5, this means that one of the nonmetals has a sufficiently larger electronegativity so that the electrons are definitely pulled closer to one side or to one atom rather than the other. What this means, even though nitrogen is not strong enough, its electronegativity is not sufficiently greater than hydrogen's to fully cause hydrogen to lose its electrons. Here, even though the electrons are shared, they are shared unequally because the electrons are closer to nitrogen than hydrogen. Now, what this results in, because the electrons are closer to nitrogen and because all electrons have negative charge, that means that nitrogen has more negative charge than hydrogen does, even though nitrogen won't have a full negative charge. Meaning that because nitrogen is technically gaining electrons, even if it isn't a full transfer, this gives nitrogen at least a partial negative charge. Now, the other way that we can look at this is from the perspective of hydrogen. Because these electrons are being pulled away from hydrogen, we can kind of say that hydrogen is losing electrons, even if the transfer is not complete, which at least partly gives it a small positive charge. this phenomenon where we have a polar covalent bond is what we call a dipole, which we can represent using this symbol here. So this symbol here is the lowercase Greek letter delta, as opposed to the uppercase Greek letter delta that means difference in. So the lowercase delta here, D is for dipole, indicates that there is a partial charge as a result of unequal electron sharing here. Now, we're going to do the same thing with oxygen and hydrogen here, so let's calculate the electronegativity difference between oxygen and hydrogen. And if we do this, we can see that this number is even greater. So what this means, and we can see that simply by looking at electronegativity constants, is that oxygen has an even greater ability to pull electrons towards it, meaning that the electrons not only are closer to oxygen than hydrogen, but oxygen is able to pull them even closer to itself than nitrogen is. Now, if oxygen is pulling these electrons closer, this is going to make its partial negative charge even stronger than that of nitrogen, because it is even better at gaining electrons than nitrogen is. Now, this also means that hydrogen is going to lose a greater share of the electrons, meaning that the electrons are pulled even farther away from hydrogen, and this is going to give it an even stronger positive pole here. Now, because electrons don't actually sit in the same place, because they are constantly moving, the other way that we can represent a dipole is using something that we call a dipole vector symbol, which simply looks like this. Remember that the word vector simply is a word that means direction. So we represent it with an arrow showing the direction where electrons are moving, and then we kind of put a positive sign here to indicate which side is losing electrons. So once again, the dipole vector symbol would look like this. And again, this is simply meant to indicate the movement of electrons. In the next video, we're going to go into more detail about how we can use delta En, or electronegativity difference, and identification of polar covalent, nonpolar covalent, and ionic bonds in order to determine what kind of bond is formed between actual elements in actual compounds.